Hello, everyone. How is everybody? Can someone confirm that you can hear me and you can see my screen? Hello, everyone. Can somebody confirm that you can hear me and you can see my screen?
Yes, you're all good.
Oh, thank you so much. Okay. Any questions? Just to adjust my computer. Okay, today we are going to go over second textbook, chapter 11, Advanced Forecasting Methods. So we are going to go over 4 sessions. Session 1, complex seasonality. In the past, our data, if they have a seasonality, it is either maybe weekly data or monthly data, quarterly data. So just one seasonality. And here today, we are dealing with multiple seasonality. For example, data has a daily seasonality, also has a weekly seasonality. This happened in call center, hospital administrations, etc. And then in session 2, we'll talk about vector autoregressions. So far, our model is based on variable x and y. So usually we say x affect y or y is decided by x. But in real life, sometimes x and y are interact each other. So x affect y, at the same time, y affect x. For example, usually we are saying income affect consumption, but sometimes consumption also affect income. So that is the vector autoregression we are going to talk about. And for the neural network models, this is it is a nonlinear regressions, and we are going to learn about neural network architecture, neural network autoregressions, and I will use example for the sun spots. Okay, the last section is the bootstrapping and bagging. We are going to use simulations to generate multiple samples of similar data. Okay, so that is the overview of what we are going to do today. Okay, so let's go first session. Complex seasonality. As I said before, this session we are dealing with multiple seasonality. When you have a call center, call volume in call center, in our example, we'll see the data experienced day seasonality and week seasonality. Okay, we are going to use a data. The data name is calls, CLL calls, and the method we are going to use is MSTS, stand for multiple seasonality time series. So this class help us to do multiple seasonality. Okay, and how many data we have? If you check how many rows you use this command in R, we have 27,716 data. Okay, so a huge amount of data. And this data describe the call arrivals every 5 minutes. Every 5 minutes from 8 a.m. to 9:05 p.m. Okay, 5 days a week and for 33-week period. Okay, so if you count from 7 a.m. to 9:05 a.m., how many 5 minutes? How many 5 minutes between 7 a.m. to 9:05? The result is 169. So this is the daily seasonal pattern with the frequency 169. And also this data has a weekly seasonality. So 1 week is 5 days, 5 working days. So for the weekly seasonal pattern with frequency, that is 845. Okay, so that is the background information about our data. Now let's dive into the ARC Studio. So I'm going to open my R. Each time when you restart R, you should load library. Library bracket FPP2 stand for forecast, practice, and principle. Principle and practice. Okay, so load this library. Okay. So those are the warning. You can ignore it. And now we are going to check. You can use this command, view calls, to see what is the data looks like. So those are the data, tons of data, okay? Those are the numbers. And then if you want to see how many records in this data set, you use n row, means number of row, and you get this number, okay? So far so good. Okay, so what we are going to do, we are going to create sequence chart, and this chart will show 33 weeks, but we don't want the time span will display week 1, week 3, week 5, week 7, etc. That's why we have this parameter by equal to 2. So every 2 weeks, okay. This is one chart. Another chart, we want to see 4 weeks, okay. So we want to see 4 weeks to expand the data. And we are going to put the 2 graphs into one place, use Grid Extra. You need to install Grid Extra package, okay. So let's dive in to produce this code. So now you have this diagram on right-hand side here. You have calls in week 1, week 3, week 5, etc. Okay, and the bottom chart shows 4 weeks. Okay, 4 weeks. In the bottom part, you have by equal 0.2. So just want to explain here. Try to move my window around. This by equal to 0.2 here means 1 week have 5 days. Okay, when you see the grid here, it is give you 5 units. You can't see it. It's actually from 1, 1.2, 1.4, 1.6, 1.8, and 2. That is the meaning. Means you want 5 units, 5 days in a week. Okay. So that is we get an idea. The data is ups and down, experience the daily seasonality as well as the weak seasonality. Okay. Next, we are going to use decomposition. We are going to decompose the data into seasonal, trend, and remainder components. Remember when we studied the first textbook, chapter 5, we did it by hand. We did it by hand based on the formula. And now in RStudio, you just need to use this function, MSTL. MSTL, we can decompose a time series. Okay. The result would be this after you issue this command. This percentage is the pipe, means you take a course data as input, put this data into this module, this class MSTL, and put the result, there is another percentage, put the result into auto plot. Okay, so this is this command does. So let's go to the R code. See this part here, maybe. So you decompose. This is the original data. This is the trend. Okay, those data over 33 weeks. This is the seasonal, daily seasonality, frequency 169. And this part is weekly seasonality with the frequency over 800. Okay, and then the last one is the remaining part. So just use MSTL will decompose your data. Okay, this is the result. Okay, I put it here. If you want to get the result of this model, you submit this command. Take course data into MSTL model and put the result in summary function. Okay. So if you go issue this command, move this a little bit. And you will see some summary data, okay? Summary data about using this function. So any questions so far? So far we just explore this data, experience, daily seasonality, weekly seasonality, okay? Next, we are going to use ETS. Oops. Using exponential smoothing, okay? Combine this one with the core data. So we did STLF stiff, we did the result into here, and the ETS has 3 parameters. The first one is the error, second one is the trend, and for the error, it could be A stand for additive, M stand for multiplicative, and for the trend, it could be N stand for non, A additive, okay? And the seasonal, it could be N is stand for non, means no seasonality, A additive, M is multiplicative. So detailed information about ETS, you can check out this information here, okay? So here you just need to know the ETS is a model have take trend, seasonal, and error as parameter. So now if you go to, this is, I just showed you here, okay, the R result. If you put the result into summary, you'll get this result. I'm not sure if you can see this result. I already showed you in R code, put the result into the C summary. If you have summary. All right, so if you use it to do the forecast, use STLF, you can issue this command, this one here, cos then percent greater than percent STLF, opening closing bracket, and put the result, you'll see this result. Okay, do I have the command here? I can copy. Yeah, I have here. So if you just copy this. So what does this? It takes cos data into STLF model to do the forecast and display the forecast result. You usually use the bracket to display the result. So those are the result, forecast result. Okay. It has the point forecast, and also it has the lower end, upper end using 80% and using 95%. This is the result. Okay. So it is here. Okay. So far we use STLF to forecast the data that has a daily seasonality and weekly seasonality. Okay. Next, we are going to introduce dynamic harmonic regression with multiple seasonal periods. And we are going to introduce Fourier terms. We are going to use the same data, call center data. Remember, call center data has daily frequency 169, weekly frequency 845. So the Fourier terms, sine, cosine, will be in this format. Okay, so this is the Fourier terms we are going to use. Specifically in R code, we are going to use autoregression. Okay, and take the data is cos. Okay. This seasonal, we assume it is false because we want to use Fourier terms to capture the ups and downs, the sine, cosine. Okay, and lambda equal to 0 means we want to the forecast to produce a stable positive result. Okay, and because we are going to, this is X, okay, we are going to produce actually 10 set of this sine, cosine, okay, and put the result into the fit, and then use this fit, use this result to forecast. And the forecast result will be into a chart, auto plot. So this is what this code does. When you do forecast, how many days ahead we forecast? We forecast 2 days ahead based on the 5 days. Okay, we focus 2 days ahead. So I'm just going to copy the whole set here and go to the R code. Just my computer. It will take a while to produce this one. Oh, this one I have notes. This command will run forever, so I'm going to kill this command. I waited for actually almost 1 hour. It didn't, maybe my computer is not that powerful, or maybe there's a huge of the data. The Fourier terms takes lots of a long calculation. So I'm going to use ESC to exit this command. ESC on top left corner of your screen. Okay, I killed the command because it takes forever. So for Fourier terms, because in the code we have this Fourier, okay, Fourier, and this Fourier, there are 3 parameters. The first one is the data, okay. The second one is maximum orders for Fourier terms. The second one, okay. In our case, the maximum term for Fourier term is 10. Okay, this is the second one. And the last one is the number of period ahead to forecast. In our case, we want to forecast 2 days. Okay, so that is the Fourier. Because we include Fourier term, this model becomes dynamic harmonic regression. Okay. So this is, if you have patient wait, maybe I don't know how long, you can produce this result. Okay. Let me see, is this the same as this fit? Yes, this is the result. Okay. We take, as you can see, this is the 5 day, 1, 2, 3, 4, 5. We use these 5 days and forecast 2 days ahead. Forecast 2 days ahead. Okay. All right, any questions? Let me check the message. Any questions? Okay.
Professor, I have
Yes.
a question.
Sure, Jay.
Why they're so different, like shady colors? They're like, you know, like blue, purple. What does it mean? Like, does it mean like it's gonna have different like forecasting, or why it's showing like that? Because I see you know, like a solid line, and also I see like the shaded like color. Is that like the percentage?
Thank you, Jay, for the question. Yeah, the solid line represents the point estimate. The shaded area represents the interval, data from this range to this range. So this forecast not only has, remember I showed you before, here it has the point forecast, say point. It also has, for example, 80% confidence interval estimate, 95% confidence interval estimate. Not only the point forecast, but also give you the range. Does that answer your question, Jay?
Yes, thank you.
You're welcome. Thank you for your question. Any other questions? That's a great question, great observation. Okay, so the solid line here is the point estimate. This is the upper limit. This one here, lower limit. Upper limit, lower limit. Okay, all right. So next, new model, TBATS models. This model combines Fourier terms with exponential smoothing. Okay, and also use Box-Cox transformation. What is the Box-Cox transformation? I remember I gave you some notes, maybe later, not now. So basically, Box-Cox transformation, any transformation, for example, you want to take square. You want to square a rational number, or you want to take a square root of a rational number. You want to take a logarithm, or you want to take, those are called Box-Cox transformation. What is the difference between this new TBATS model from dynamic model is that In dynamic harmonic regression model, the seasonality is not allowed to change, but with this model, TBAT modes, seasonality is allowed to change slowly. That is the difference between those two models, okay? And this code, it will take a while to run this code here. So I'm going to, if you have patience, but I don't want to spend time, I will explain the code, explain the output. You can test by yourself. Just copy this code. And then, so let's use this code because it's a huge data. We want to start, take a subset, just take a part of this data and put the part of the data into this model, TBATS model. And the result is in fit 2. Okay, after we have fit 2 model, we want to produce the next 2 days forecast. The result of the forecast is FC2. And then we are going to auto plot our FC2. So this is what this code does. And the result will be here, similar to one we get before. Okay, based on 5 days data, make prediction for 2 days ahead. For 2 days ahead. Okay. So this is this code. It will take a while, take 5 minutes. Oops. Maybe take 5 minutes to run the code. Okay. So this is this one. Any questions so far? The log transformation is belong to Box-Cox transformation. So this one is still from that code. Okay, so this is the TBATS model. Any questions? Okay. Complex seasonality with covariance. The TBAT models do not allow covariance. Covariance means variables can change together, but this model does not allow variables change together. But they can be included in the dynamic harmonic regression model. So this is the code. Okay. This one we use a different data. The data is elect demand. So let's take a look at what is this data looks like. So if you want to see what the data looks like, you type in VREW, the first letter is capitalized, then elect demand. Okay. Double check my spelling for the data name, ELEC, elect demand, small letter D. Okay. Small letter D. Let me double check. I remember it. Small letter D. Yeah. It is case sensitive. So this is how the data looks like. Elect demand. It has 3 columns: demand, electricity demand, work day. If it is work day, it is 1. Non-working day, it is a work day is 1. Non-work day is 0. If you scroll down, you see some ones. Okay, and the temperature is the temperature for that day. Okay, so this is a data, again, a huge amount of data. Okay, so this is the elect demand data. If you want to create a sequence chart to explore this data, you can use autoplot. You can use autoplot. To produce, oops. So this is how this data looks like. I will move this. You see, you have demand, you have a temperature. Looks like when the temperature is high, the demand is high. And also when temperature is low, the demand is also high. It makes sense. When temperature is high, people use air conditioning, okay? Use more power. And when temperature is low, people use the heater, also increase the demand, okay? So this is how the sequence chart looks like for the elect demand data, okay? Of course, it has ups and downs, okay? Looks like there is a nonlinear relationship between demand and temperature, So this is the result, okay? And next, we are going to put the temperature as X, demand as Y, use temperature as X, demand as Y to produce a graph. So this graph, we are going to use ggplot, and take elect demand as data frame, okay, produce that result. So let's take a look at the R code result. Okay. So clearly, it is not linear. It is like curvaceous. It is curved, looks like, okay? So the y-axis is the demand, x-axis is the temperature. You put two variables in one graph. And this is the result, okay? Next, we are going to use the piecewise linear function of temperature. It contains 18 degrees, okay, and a harmonic regression terms to allow for daily seasonal pattern. Okay. So this function is the piecewise function. P stands for piecewise. We are going to take elect demand. This is take this data. We are going to, it is a focus on temperature variable, okay? Allow for temperature is 18 degrees, okay? And again, this one will take a very long time to run this code. So I have the notes here, take longer time. So I will explain this, okay? So what we are going to do, we are going to use elect demand. This is our original data. The demand is our Y, okay? And we are going to use the Fourier terms as our X, Fourier terms as our X, okay? To fit the ARIMA model. The result we are put into the fit. Okay. And then we are going to forecast up to a week ahead. Use repeat of the last 2 days temperature. Okay. So this one means we forecast 2 days ahead. Forecast 2 days ahead. And put the forecast result into FC variable. And then we plot this FC variable. Okay, if you just copy this code, and then copy this code, you will get this result here. Okay, so those are the existing data. The blue one is the forecasting data. Blue one is the forecasting data. Because it will take longer time, I will omit the demonstration part. If you're interested, you can just copy the code into the R command. And then when you check the residues, so just issue the command, check residues of FC, you will get the picture about the residue. Looks like it's not too bad because the residue has the normal distribution here. Okay, but the residue is not perfect because there are spikes when you take a look at ACF function. Okay, so this is a session 1, multiple seasonality. We want over 2 examples. One is the call center data. The other data is electricity demand. Any questions? Okay, so next we move on the second section, vector autoregressions. So far, our variable, we have a clear picture which one is my X. For example, income is my X, consumption is Y. Okay, so we are saying income affect consumption, but sometimes all variables can affect each other. Consumption can affect income, income can affect consumption. Okay. So we are going to use capture this relationship using VAR framework, stand for vector autoregressive framework, to allow X, variable X affect Y, Y also affect X. And the forecast is generated in recursive manner. Okay, recursive manner means it is built the steps based on the previous steps. Okay, and we introduce some notations. We use capital K represent number of variables. Small letter p represent how many legs. Okay. The VAR model, we are going to use VAR packages. Okay. So that is the overall introduction about vector autoregressions. It is useful, this model vector autoregression is useful for the following 4 contexts. You can read by yourself, it's pretty straightforward. And pay attention to this formula. The final exam will have question about this one. The number of coefficients needs to be estimated in vector autoregressive model is equal to K plus P times K squared. Remember what is K? K is how many variables? Number of variables. And what is P? Time legs. How many legs is P? Okay. Okay, so let's take a look at an example for US consumption. Remember last week we used this data, the US change. So let's take a look at what this data looks like. VREW view, US change. This is the data. Press enter. So this data have consumption, income, production, savings, unemployment for many, many years. Okay, or many, many quarters. So this is this data. Now we are going to propose 3 models. For this data, propose 3 models. And then pick the best model out of these 3 models. Model 1, but before we do this model, we need to typing this command, library VRS, okay, and then we are going to show to get the lag length using this command. You can just copy this together. So we get this result. If you use AIC criteria, you need 5 lags. And HQ1 criteria, SC is 1, FPE is 5. Okay. So that's why we produce 3 models, okay, based on this information. So model 1, we just take 1 lag. Just take 1 lag. And then using this VRI vector autoregressive. And then we are going to do the test, serial test. And the test statistic, we are going to use Portman test statistic. Portman test statistic. I have a note here. So it is a Portman statistic. Okay. So this is model 1. Okay. Next, we are going to produce model 2 based on 2 lags. 2 lags. Again, we are going to produce Portman test statistic. So just copy this code. You are going to get model 1 and model 2. Okay, so this is from model 1. The p-value is 0.07. In this case, we need the bigger the p-value, the better the model. So this is 0.07 p-value. And our model 2 produce p-value 0.03. Okay, not good, both 2 models. So next, let's propose the 3rd model. Okay, so the first 2 models, they all have the residual correlations because p-value is not big enough. Okay, p-value is not big enough. Now we produce lag 3 model, lag 3, and use Portman test statistic. So just copy this. So this time, you see the p-value improved a lot. P-value improved a lot from 0.03 to 0.2. Okay, so we decide to use the 3rd model. Use the 3rd model to do what? To do the forecast. Okay. So how do we do forecast? We use the 3rd model, do the forecast, and put the result into the graph. Put the result into the graph. So this is our it takes several minutes. Take some time. Yeah, it's not that long. So this is the result. See, we use the 3rd model, VAR3. Okay. Because we have 2 variables, consumption variable and income variable. This the end part here is the forecast. So we have this solid line is the point estimate. We also have a lower limit, upper limit. Same thing happened for income. We have point estimate. We have lower limit, upper limit. Okay. And if you want to know, this is the graphical representation of the forecast. If you want to know the number format, you want to see the number, forecast number, what do? we did a couple of times last class. You want to see the number, not a graph. You want to see the forecast number. What do? You put the bracket, okay? You put the bracket, you can get the forecast. See, you just put the bracket. You can get the number forecast. Okay, so just copy this into R. See, you get, by the way, the original data is quarterly data. You get the point forecast. See, for the consumption, the point forecast for 2016 Q4 is 0.712. Those are the lower limit, upper limit when you have 80% confidence interval, and those the lower limit, upper limit when you have 95% confidence interval. Okay, so same thing happened for the income. So this is the number format. Here is the graphical format. Okay, graphical format. So I did this. Okay, so that is a session 2, vector autoregressive model, VAR model. We use US consumption data, proposed 3 models. We select the last model, model 3, and use this model 3 to forecast in graphical representation and in number representation. Any questions? Okay, shall we take a break? After break, we'll do session 3, neural network models, and the last session, the bootstrapping. Okay. Shall we come back at 7:30? 7:30. Okay, so I'm going to type in this information in chat area. Okay, break. Back at 7:30. I'm going to stop recording. When we come back, I will start recording again. Where is my recording button? Stop recording.